Okay, we're going to look at theorems, looking at angles in the circle. So looking at different kinds of geometry. Now, I'm not going to go over the full proofs for the theorems because that's a very long video, and I might not even do that at all. I'll probably do some proofs later on, but not just now. Today, purely theorems for angles in the circle or circle geometry. So we have theorem number 1. Now, I'm not going to write the definition because it's pretty long. I'm going to explain it a lot faster. So theorem 1, this is our code for that theorem, represents that this essentially says that the angle subtended at the center of a circle is twice the angle subtended at the circumference standing on the same arc. What does that actually mean? So the symbol, like I said, or the code is like a little arrow. What that essentially says is if I have a circle like this, and now this is the important part, it has to have two different things. First of all, needs to be the origin, and what we'd be looking for is this angle here. Now these lines have to join up to the origin, so let's say I have these two angles, one at the top and one down here. So the theorem says the angle subtended at the center of the circle is twice the angle at the circumference standing on the same arc. There's two things we are looking for. First of all, that the angle is being formed at the center of the circle, or the origin, so right in the middle. Then we're looking for two angles. We're looking for one angle sitting on the circumference. So in this case, this angle sitting out here on the circumference of the circle, and the other angle sitting again, as I said, at the origin. And what this theorem essentially states is, I forgot one important thing. The next part of that is that we have those two angles, and then the next part of that is that they both share the same arc. Okay, so they both stand on the same arc. I like to use the word stand. I imagine two little feet standing up. So let's look at the arc for both of these angles. So as you can see, this angle connects to the radius here. Well, it has two radius essentially because they're both connected to the origin. So its arc is going to be sitting along here. Now let's look at our top angle as well. We follow down, point here, shares the same arc. So if it ticks all those boxes, as in the angles formed at the origin and one on the circumference, and they share the same arc, it means that this angle here, so if this was x, would be 2x. It would be 2 times whatever that angle is there. Now this can present in a couple of different ways. So there's the more obvious arrow-like formation, I guess you would call it, but it can also present something like this. Let me just have a little draw. So remember, the key to this is that they share the same arc, and there's an angle on the circumference and an angle at the origin. So let's say I had something like that. And now this doesn't necessarily join up to the origin, it goes down here. So say for example I had an angle in here. Well, let's look at our two criteria. And let's say we're trying to find this angle under here in this little space. Okay. Let's look for our two different criteria. First of all, do I have an angle that is subtended at the origin? So it's sitting around the origin of the circle, and yes, that's one angle that I have. The next one is, do I have an angle made up on the circumference of the circle? Well, yes, I do, right here. Now the next big thing is, do they share the same arc? So I'm going to get rid of that just to illustrate the point. This angle here comes down here, and it has standing on that arc there. So we look at this angle here. Well, there's a point there and a point there. So it is actually standing on the same arc as well. So that means if that angle was x, it means whatever angle in here, this interior angle, would be 2x, or whatever that is. That's theorem 1. Pretty simple stuff. Let me rub this out. Okay, so theorem 2. Again, I'm going to throw the language at you, but it doesn't necessarily, well, it's going to be represented by a little code. So let's go theorem 2, and our code is this little circle-y thingy and a nice little crisscross. And what that represents is the fact that all angles that have their vertex on the circumference and are subtended by the same arc are equal. Okay, so let's have a little look at all this is really saying is, so I'm going to draw that there, that one's going to go there, let's draw another angle like that, and let's draw a third one just for fun. Let's say I had X sitting there. All this says is, now notice I don't have an origin, these aren't passing through the origin, but this says all angles that have their vertex on the circumference, so vertex on the circumference, vertex on the circumference, vertex on the circumference, yes, 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 are subtended by the same arc are equal. Well, let's check the arc. For this angle here, its arc goes from here to here. So it shares an arc with this angle on the vertex here to here, yes. And this angle here, its point is on the angles on the vertex, and its arc is there to there. So it shares the angle. So all this says that all of these angles are actually going to be equal. Again, there's nothing to do with the origin here. That's a big giveaway. They just need to have points on the vertex and share or stand on the same arc. That's a nice plane going over that you can hear, but that's all that theorem says. So let's look at a little example with both of those theorems in play. So let's pretend that we had a circle like this. We have an origin, so we do have an origin like that, but then we also have another one crossing over like that. Oh, I'm going to straighten this line up a little bit. So we have the origin, we have a couple of lines crossing over like that, and we have them joining up like that. Okay, that's a little O there. I apologize for the raggedness of this. It's hard with whiteboard markers. So let's say I had an X there, so I want to find X. Let's say this angle in here is 46 degrees. Now, if I wanted to find out what all of these were, let's also include a little y down here, we just have to look at our little theorem. So first things first, let's deal with this X, okay? Now, we notice that this X is on the vertex of the circle, and it has this stands on this arc down the bottom here. Now that's the same as this 46 degrees. Its vertex is on the circumference, and it stands on the same arc. So therefore, we can say X equals 46 degrees because of our second, didn't draw that properly, because of theorem 2. Okay, we established it met both the criteria that we needed to actually say that X is going to equal 46 degrees. They stand on the same arc, both points are on the vertex. What about Y? Well, Y is going to equal 46 times 2, which is going to be 92 degrees. Now, we can justify this because our theorem 1 says, remember, if we have a point on the vertex standing on the circumference, and the angle is subtended at the origin, so you have an angle at the origin, an angle on the circumference, then that means that this angle here at the origin is always going to be 2 times whatever this angle is here. So I've taken 46, multiplied it by 2, equals 92 degrees because of, and that's where we can draw our little theorem 1 code, so we don't have to give the full explanation. So that's the first 2 theorems done and dusted. Now the second 2 theorems, also pretty straightforward. The language is a little bit confronting, but nothing too bad. So if I had, let me just write my little theorem 3 sitting there. So here's my code. Draw a little semicircle like that. Come out. And that's going to come down like that. Oops, sorry, that should, yeah. Let's draw that down like that. Yeah, it looks a bit better. All right, so that's my code for theorem 3. Now, theorem 3 says angles subtended by the diameter, or an angles in a semicircle, are right angles, or always right angles. Now, all that's essentially saying is, if I have myself a semicircle, and my angle goes from one point in the diameter, so straight across through the center of the circle, as big its width, to the other point of the diameter, no matter where I go from, all that's saying is that these angles are always going to be 90 degrees. Okay, one part of the diameter over to the other, this angle will always end up being 90 degrees. Pretty straightforward theorem. And theorem 4 kind of borrows or is in the same spirit, looking at right angles, but your code for theorem 4, now we're going to start using tangents, something like that. So theorem 4 just says that if a radius is drawn to any point on the circumference, so a radius, this is coming to the origin, okay, so it's a radius drawn at any point in the circumference, and a tangent is drawn, so a tangent is a line that runs on the external on the circumference, but only hits at one point. At the same point, then the radius will be perpendicular to the tangent, so at a right angle. So all it's saying here is if I draw myself, so that's a radius, looking to the origin. If you draw yourself a perfect tangent here, saying that is going to be perpendicular or at a right angle. So that means this little angle here will be a right angle. So what would this look like in action using these two theorems? Well, let's get ourselves a little example problem. So let's say I had a circle that looked like this. Okay, now I'm going to draw a diameter across there, have my origin sitting there, and I have a little triangle that goes like this down to there. Sorry, that line's not as straight as it could be. And then I have a straight tangent going down along there. Now, there's a couple of points that I want to get. That is Z. And I'm also looking for this angle here to be S. Okay, now, I want reasons for this. I want reasons. But I'm going to go straight ahead and say that Z is going to equal 90 degrees. Because this starts on one part of the diameter, is subtended somewhere in a semicircle, and ends at the other side of the diameter. That means that angle Z is going to be 90 degrees because of our third theorem there. Okay, pretty straightforward. Now looking at S, again, we have ourselves a tangent. So we're going to say S equals 90 degrees because of, well, our fourth theorem. Because our fourth theorem states that if you draw a line perfectly from the radius, then draw a tangent that meets it at one point, that's the definition of a tangent, then that line is going to be perpendicular, so therefore at 90 degrees. So both of these end up just being 90 degrees. Pretty straightforward stuff there. And last but definitely not least in our theorem list, theorem 5. Theorem 5. Now, this one, the way I remember the symbol for this one is it's kind of like a little sideways hat. So draw something like that, and then I need to draw, I need to come all the way out, and I need to join to the same point. It's really important. You join to the same point there. Okay, now what this theorem says is that the angle formed by two tangents, so tangent here and a tangent there, meeting at the same external point, so one different point or one external point out here, is bisected or cut in half by a straight line joining the center of a circle to that external point. So this is going to be our origin of our circle, and it's going to go all the way out to this particular point. Now, the best way to understand this theorem is to have a little look at an example. So I'm going to draw my little example here. All right, hopefully this will be clear enough. So there's my circle. Now remember, I'm joining the same external point, so I'm going to draw a tangent here, a tangent there, both joining up to this same point. Now this says that I can actually bisect it from the center of the circle, or the origin, just like that. And then my two triangles are going off like this. Now I'm going to have a lot of different things I'm trying to find. I'm going to be T, U. We know this is going to be 68. Hopefully you can see that well enough on the camera. This is going to be angle R. This is going to be angle Q. And this is going to be angle S. Okay. Now let's also label our points just so we have something to work with. C, B, and A at the top here, and of course that's always going to be our origin. Okay, we have a fair bit to work out, okay, but straight away I can see another one of our theorems in this that's going to make our lives a little bit easier for ourselves. I see a tangent and I see it joining the origin, so forming a radius. So that means that S is going to equal R, and they're both going to equal 90 degrees. Because of our, which one's this one? Our fourth? Yeah, our fourth theorem, sorry. Now, if we look here, that's because we're joining up to the origin here. It's going out and it's hitting with a tangent, okay? So whenever this hits with a tangent, we know that's going to be 90. We know that that's going to be 90 there. So we know that both of those are going to be 90, okay? Now, we know we have two values in the triangle, 68 and 90. So we know that the triangle ABO has to equal 180 degrees. We know that about triangles. So therefore, to get to 180, it's going to be 68 plus the 90 that we found out, plus whatever T is, has to equal 180. So that means T, or our value for T, is going to be 22 degrees. Okay? So we found that T is going to equal 22 degrees. We know that R is going to be 90 degrees. We know that S is going to be 90 degrees. Pretty straightforward. Now, this is where our theorem comes into play. Now, ABC, so this whole triangle here, is formed by two tangents. So thinking back to our theorem 5, well, we need two tangents. We've got that, and they're meeting at the exact same point, at the vertex B, right here, meeting at the same point. And we've bisected it with the center of the circle, or the origin, and that means that the angles T and U have to be equal. They've got to be equal. Okay, so U is going to equal 22 degrees, and we'd say because of our fifth theorem. Now, we can establish that both of those triangles are exactly the same, but we're just going to use some simple logic to get our value for our for Q, just sitting on the inside. Now, hopefully this will come up big enough, but we're saying that essentially in the triangle AOB, so this top triangle, well, we know that it's going to have to equal triangle COB because they're two tangents looking at theorem 5, essentially. So we know that up the top here, R plus S R plus T, R plus T plus 68 is going to equal 180 degrees. So that must mean that U plus S plus Q have to equal 180 degrees. Now let's substitute in the things we know for sure, that we've proved already over here. So we know that R is going to equal 90 degrees, plus T is going to equal 22 degrees, plus 68, which we already know, is going to be 180 degrees. Now let's use what we know here already as well. Well, we know that S is going to be 90 degrees. Actually, let's start with, I should have been ordering this according to the letters here. I'm just running out of space. But let's start with U, like I have up here. We know U is going to equal 20 degrees, plus S has to equal 90 degrees, plus Q, it has to equal 180 degrees as well, because all of those have been proven previously. So therefore, our value for Q in this instance has to equal 68 degrees. We don't have to do anything extra to prove that because we've proved all this stuff beforehand, so we can make the assumption about Q based on what we know about triangles. Those are the 5 theorems with some examples. I didn't do any proofs for those examples. That might come in a later video. There we go, we're done.